memory address what data it puts in. So that is the one thing. Number two, it also talks about tree placement algorithm. Tree placement algorithm happens very frequently in microprocessors CAD system because the system wanted to throw away unused, unused or least frequently used data or address from that particular storage. Okay, so let's look at the architecture. This is architecture in whole. The process is connected to the cache controller by sending the same control signal. So it does not know whether it's connected to main memory or cache controller. The cache controller is then connected to the cache memory. So when the cache miss happen, there is a copying from the main memory to the cache memory. We call it that information mapping happen in three different technology: associate mapping, direct mapping, set associative mapping. In this three methodology of mapping from main memory to cache memory, what happens is the address, the different type of address is being stored in the cache memory. Okay, this reflects the address. Give me 1 minute again. I wanted to go and refresh myself. Hello, Monica. It is raining over here. I thought we are having a stable internet connection. Are you having a stable internet connection? Hello, hello. Mic testing, mic
Yes,
testing,
sir.
mic testing. Okay, so next we wanted to look at the catch read operator. This is a very simple process taken from the textbook, and I never asked in the what you call midterm or final exam. This shows you catch hit. This is catch hit and catch miss. Catch hit. The process is the cache controller will read a real address from CPU. Okay, and then next step is the cache controller. We check whether the block. What is a block? We look at later. Cache line contains the relative address or real address or not. If the address is available in the cache, then data will be read from the cache directly into the CPU, and the process is done very fast. If the data is not available in the cache, then the system, the cache controller will access the main memory for the block containing that particular real address. It will read and copy to copy one to CPU, another copy of it will be stored in cache organization in cache line. This is how it works basically. Next, we wanted to show you the progress of cache. Progress of cache. Uh, what you see is over here how the size of the cache grows bigger, and you also have seen how from one level cache becomes three level cache. I'm seeing that it was introduced in 1968 by mainframe, and of course when you say cache in 1968, we are talking about a very huge price for that particular computing system. This has been completed until 2011. What I want you to do is I want you to complete until 2022. You can take Intel as your example, and I want you to complete. Show me the table in the next class. put what do you call write on the write on your notebook, or if you can find similar tables on web, I want you to print and paste on your notebook and show me. Okay, we want to see after 2011 and 2022, in the span of 11 years, how the catch has behaved. I mean, the system of the catch has been grown up to something very complicated. Next, we wanted to see how two architectures, how has been implemented. Architecture number one is for microprocessor known as Dual Core 2. Dual Core 2 is a microprocessor was introduced before I processors, and it was introduced for a very short period of time before Intel upgrade to Intel Core processors. So in this example, we have two processor, multiprocessor system. In the multiprocessor system, there's two cores and core two. The name is core two. There was core zero and core one. Each one of them has its own processing element ALU, and each one of them has its own L1 cache. While L2 cache are shared by these two cores. These two cores share L2 cache, and in dual core two system, we have only L1, L2 cache system. This is another architecture, i7 3 level. i7 not the current technology, not the current processor, but it's, I think this is seventh generation if I'm not mistaken. So we have four cores over here, core one, core two, core three, and core four. Each one of these core has been built with uh, level one cache. You have two different type of level one cache. One type is to store only instruction, another type is only to store data. So question comes sometimes I receive good questions where I'm not able to answer. For example, I received one good question a couple of semesters back, and he was referring to DIB. He said the DIB is connected to L2 cache. Does it mean that each core has one cache? Like before we have four L2 caches located outside. So I said no, that DIB may be referring to L3 cache. Different microprocessor has different architecture because L2 already implemented or embedded as part of core over here. Okay, so the level one cache consists of two caches, instruction cache and data cache. So we have 32 plus 32 is 64, 128, 256 kilobyte of level one cache. Level 2 cache is shared cache, consists of the instruction and data. The size is 256, 256, 256, 512, 1 gig. So I have 1.256 cache already. L3 is 8 megabyte, shared by all four cores. And what I'm interested to know is, does this applicable on modern processors, modern L? So you have to answer that by completing the diagram. Okay. So totally that's 500 to 12 kilobyte L2. Okay, then we want to talk about cache architecture, cache structure. I will stop my classes after this because I want to synchronize with the morning class. In the morning, we stopped until main memory, but in the morning, I took so many breaks. Munira, I think, I think you break yam la lot. That's why you feel sleepy. Am I connected, brothers and sisters?
Yes, yes.
Okay, Alhamdulillah. So what are we seeing here is a catch structure. The catch consists what we call line. This is known as one line, two line, three line, four line. So this example has C number of lines. So if you ask me why C minus one, because we start with zero, we ended up in C minus one, but totally we have C number of lines. So each line has three components. The first component is known as tag. Tag consists information and addressing. For example, this is one block. For example, this is one block. Let's say 0 until 5 is one block. So the memory of address is mapped to the tag. This is what we call mapping technology. The mapping technology decides how the tag supposed to store the memory address. Okay, memory address. So we have three different type of mapping, and the block consists data inside data. Right? Let's say I have five words over here. The content of five words is copied to block, while the tag consists the address, and now I have one more which is not shown over here, which is flag control bit. The flag decides how many times particular address has been accessed, how many data has been read. That is the function of the flag control bit. Okay, so let's look at our coming back to this thing. So each line, my cache memory is divided into lines. Lines or blocks. Each line can range from 16 to 64 byte, depends on the microprocessor. Data is copied into blocks. Right? If data is copied into blocks, then what is the function of tag? Tag is to store addresses, part of addresses. It doesn't say addresses. It doesn't say address, it's part of the addresses. How it is being stored, the part of the addresses, that depends on the mapping technology. While we have another component which is not shown in the control in the cache structure, which is known as flag. We have a small calculation that is to determine the size of a cache, or how the formula is number of bytes stored in data block multiplied by number of block. Meaning to say that if we have a size of the block, size of one block multiplied by number of lines multiplied by number of blocks, then uh, that is your total size of the cache. Example as given, if an IP4 has a L1 of 8 kilobyte big K with 64, this is the total size. Yeah, I think this is big B, not small b. It's 64 byte. How many blocks it has? Simply the total storage 8 KB divided by 64 KB, and you will come to understanding that it has 128 blocks. There are more information over more calculation over here, which I can't embed to disclose. So again, this is the cache structure. Okay, next we want to start our memory, but as I told you just now, I 2:40. Yeah. We'll take one more minute break and we'll come back now because our class finish at 3:20. Are you okay? This is where I stopped in the previous class. Are you there, Mr. Munira, Miss Munira? Am I disconnected? Am I disconnected? So since we have time, I wanted to take 1 minute break. You also take 1 minute break. Basically, literally, I'll be sitting here. I'm not going anywhere. Okay, brothers and sisters, I think we should stop our class over here because we want to synchronize our class with the previous morning section, and we supposed to do a quiz on Friday, but people say no, I don't want the quiz on Friday, so I'm planning to give the quiz tomorrow on chapter 3. So please let me know, and we will discuss that in our group. Okay, with this, Assalamualaikum warahmatullahi taala wabarakatuh.
Waalaikumsalam. Thank you, sir.
Thank you, sir.